All right, so today we are going to continue. This is Math 383 complex analysis. What we're going to do is we're going to talk a little bit about from Cauchy to the Gregory-Leibniz formula. We'll talk a little bit more about continuation of the Riemann zeta function. So right now it keeps it as a tie between the two. We'll talk a little bit about Poisson summation, which is one of the key ingredients that's needed to complete the proof that we were talking about last time. Now, we had given some easier proofs that allowed us to continue to the real part of s greater than 0. But to get all s, we had to do a little bit more work. And we noticed that there were some interesting features. There was this 1 over s minus 1. And there's the question of where are the poles? Well, the gamma function has a pole at the negative integers and at 0. And that's going to pass on information to the Riemann zeta function. And then we're going to start talking a little bit about Fourier analysis. So Fourier analysis, we've actually seen this already. We've been doing it for a good chunk of the semester. We've been trying to calculate certain integrals, and those integrals just happen to be Fourier transforms of standard probability distributions. And so this is one of the greatest applications of complex analysis. It's to compute stuff like this. One of my favorite ways is to essentially cheat and just have some kind of free variable and do it in the real case, and then say by an accumulation theorem, we now know it when the parameter is complex as well. And by appropriately choosing it, we now have the Fourier transform essentially for free. So if you've taken a class in differential equations, who has done that? So you've hopefully done Laplace and Fourier transforms to solve problems. And then the hard part about that is, you have a differential equation, you take the Laplace of the Fourier transform, it converts it to a new equation, often a polynomial equation to solve, and then you have to do the inverse transform at the end. And that's where things get a little bit challenging. So the big item for today is the power of duality, the ability to, instead of looking at the problem that you were given, to look at an equivalent problem and making progress there, translate that to the original one. All right. So the first is to talk a little bit about the Cauchy distribution. So this is somebody we have seen before, but in an entirely different setting today. So I guess all the computers I'm in today keep saying that they want to update their Java. All right, so a couple of years ago, one of my probability students gave me the following. Let me see if I can actually get this on the picture just for a second. So anybody know what this is? Yeah, truncated. They couldn't afford to buy the infinite one. So this is truncated a little bit, but it's easier to pack. So the Cauchy distribution is essentially 1 over 1 plus x squared. And we talked about why the normalization constant is 1 over pi. We talked about how we could actually calculate the integral of 1 over 1 plus x to the 2n very easily. If we do 1 over 1 plus x cubed, what's the problem with that? If we try to integrate from minus infinity to infinity, 1 over 1 plus x cubed. Yeah, there's a pole, in fact, on the line that we're integrating. And so if I want to have a density 1 over 1 plus x cubed, I just do from 0 to infinity. Or I do 1 plus absolute value of x cubed. And so there's beautiful formulas for what all these normalization constants are. Here is one of the applications for something like this. So let's integrate from 0 to 1 of 1 over 1 plus x squared dx. And then normally I teach this in a calculus class and I don't do things too carefully, but this is actually an analysis class where real analysis is a prerequisite. So I should not be just waving my hands, and I should actually do things carefully. So this is the limit as epsilon goes to 0 of the integral from 0 to 1 minus epsilon, 1 over 1 plus x squared dx. What do you think I want to save a little bit and only go up to 1 minus epsilon? Yeah, the power series converges. So I want to view r as negative x squared. So 1 over 1 plus x squared is 1 over 1 minus negative x squared is the sum and goes from 0 to infinity of negative x squared to the n. So again, a huge amount of mathematics is pattern recognition. When I see 1 over 1 plus something, I should be thinking a geometric series. And so this is going to just be the limit as epsilon goes to 0, the integral from 0 to 1 minus epsilon, the sum, and goes from 0 to infinity, negative 1 to the n, x to the 2n, dx. Now what should I do? Yeah, flip them. Am I allowed to flip them? Why? Because it converges absolutely. So whose theorem are we using? Fubini or Fubini-Tonelli, if you want to be a little bit fancy and talk about the fact that we have an integral and a sum, but we can switch them. And this is the same as the limit as epsilon goes to 0, the sum n goes from 0 to infinity of -1 to the n integral from 0 to 1 minus epsilon x to the 2n dx. All right, that's not a bad integral to do. So it's going to be the sum n goes from 0 to infinity, -1 to the n, and then we'll have x to the 2n plus 1 over 2n plus 1 at 0 and 1 minus epsilon. So it's the limit as epsilon goes to 0, the sum n goes from 0 to infinity of -1 to the n over 2n plus 1, 1 minus epsilon to the 2n plus 1. What is that limit going to equal? So for any epsilon, this is fine. What will this equal as epsilon goes to 0? I'm sorry? Well, it will equal the original integral. But what sum will this be as epsilon goes to 0? Yeah. Oh, let's be a little bit careful about using the alternating. Oh, the alternating even. Okay, as long as you said the alternating even harmonic. Okay. We have to be extremely careful because this does not converge absolutely. But what's nice is if you take every two terms, there's going to be a lot of cancellation. And if you look at what's going on every two terms, you will get something that converges. And so as a nice exercise, show that if you look at things in pairs, it's going to converge. What's wonderful about this is it's going to be an alternating sum. So it's going to be 1 minus a third plus a fifth minus a seventh plus ... So if you stop after a positive sign, you've overshot the answer. If you stop after a minus sign, you've undershot the answer. And essentially, when you look at it, it's going to look like an error of size 1 over n squared. If you look at 1/5 minus 1/7, this is 2 over 35. 2 over 35 is really just 2 over 6 squared. When you look at 1/9 minus 1/11, that's really 2 over approximately 11 squared. So if you look at every two terms, it's essentially 2 over n squared, and that sum will converge. So with a little bit of work, which I encourage you to do, you can justify all this. What does this sum equal? It's just arctangent of x at 0 and 1. And what angle has a tangent of 1? Pi over 4. And what angle has a tangent of 0? 0. So this is just pi over 4. We've done this before. The derivative of arctangent is 1 over 1 plus x squared. So that's one of the derivatives you're supposed to know. You get this using the chain rule. So just recall, if f of g of x equals x, then f prime of g of x times g prime of x equals 1. So g prime of x is 1 over f prime of g of x. So if you take the tangent of arctangent of x, that's just x. So you get arctangent prime of x is 1 over the derivative of tangent. And what's the derivative of tangent? 1 over secant squared. So actually, it just becomes cosine squared at arctangent of x. And then you just draw the triangle. And if this is theta, if you want an angle whose tangent is x, it's x. X, even x 1 square root of 1 plus x squared. And so that's then going to give you 1 over 1 plus x squared, and you do the cosine squared. So beautiful result. Here is a way to calculate pi. Or at least to calculate pi over 4, but I leave the exercise to get pi from this. It turns out, not surprisingly, that this should remind you of a function. Which function does this remind you of? Any function that we've been looking at recently that's really important? Yeah, it looks a lot like the zeta function, right? Let's get Riemann back on the board. So what do we have? We have pi over 4 is the sum, n goes from 0 to infinity, of -1 to the n over 2n plus 1. And this is the same as the sum, n goes from 1 to infinity of chi of n over n, where chi of n is equal to 1 if n is congruent to what? I think it's 1 mod 4. -1 if n is congruent to 3 mod 4, and 0 otherwise. This is the pi fourths is 1 minus a third, plus a fifth, minus a seventh, plus a ninth, and so on. So if we define this new function chi of n, this has some very interesting properties. What is chi of n times m? Chi of n times chi of n. Does this need to be proved? Yes. How many cases are there to consider? Well, there's really only 3 possibilities for n, 3 possibilities for m, right? But if either n or m is even, then it's really easy, right? So it's trivial if n or m is even. So we're reduced to the case when they're both odd. Now there's only 4 cases to look at. Well, if one of them is 1 mod 4, if you multiply something by 1 mod 4, you don't change its remainder mod 4. So, we might as well assume that, n and m are both 3 mod 4, and then you would just see -1 times -1 is 1, and something that's 3 mod 4 times something that's 3 mod 4 is 1 mod 4. Because it'll give you a remainder of 9, and 9 is just 1. Out of curiosity, who here has not taken a class in abstract algebra? Okay, good. So it's just me. Okay, so everyone, I've taught it. Don't worry, I've taught it. I just haven't taken it. All right, so one person hasn't taken abstract algebra. Okay, so there's 2 of us. All right, we can form a study group later. All right, so hopefully you've seen at least modular arithmetic and congruences. If I have 2 numbers, I can look at their remainder and I can just multiply them out. So I could write, m as 4k plus 3, and n say is 4l plus 3, and I would have m times n is equal to a multiple of 4 plus 9, which is congruent to 1, 1. So what this is telling us is that the Riemann zeta function might just be the first of a whole zoo of functions to study. And we can look at what we'll call L S chi, which will be the sum. N goes from 0. Oops. I was teaching probability earlier today. We saw all the sums there at 0. N goes from 1 to infinity of chi of n over n to the s. And it turns out this is the same as the product over primes of 1 minus chi of p over p to the s inverse. And again, there are many more L functions that you can study than just this. But it's telling us that pi over 4 can be viewed as a special value of this L function. Do you think this L function has better or worse convergence properties than the Riemann zeta function? Better. Why? Yeah, it doesn't have a pole that s equals 1. And so there's a lot of conjectures as to which L functions would have a pole at s equals 1? Do you have to basically be a multiple of the Riemann zeta function to have a pole at s equals 1? Because we have an alternating series with chi by partial summation, we might expect that we can continue this trivially to the real part of s greater than 0. That it's going to be much easier than the Riemann zeta function because we have this alternating signs. This might remind you also a little bit of the alternating zeta function that we looked at. And again, in terms of just trying to get better convergence and better properties. So again, we're not going to spend too much time talking about L functions, but I want you to at least be aware of them, and I want you to see how can you generalize. Because that's one of the key objects or the key ideas you want to get as you study mathematics. Given some problem and some results, what else can I apply this to? And what else would this be useful for? So the Riemann zeta function is very useful for studying how many primes there are. These generalizations, this is a Dirichlet L function, are useful for studying primes in arithmetic progression. And in this whole zoos of L functions that you can study that are related to a variety of very important problems. All right. Anybody here today speak German?
Sure.
Okay, you want to read it? Let me see. Starting with man findet.
Nun in der das etwa so zwei Fehler wird innerhalb dieser Grenzen und es ist sehr wahrscheinlich, dass alle Wurzeln sind. Hiervon war allerdings ein strenger Beweis zu wünschen. Ich habe in die Aufschwung derselben Nacht einigen flüchtigen Vergleichen der Suchen vorläufig bei sich gelassen, da für den nächsten Zweck meiner Untersuchung entbehrlich sein.
Thank you. I had to learn 2 out of French, German, and Russian, but only well enough to read them, not to speak them. And so the Riemann's classic manuscript was one of the papers I read. This is a paper I strongly encourage you to read in whatever language you want. It's been translated numerous times. I know my friends, I was an undergraduate at Yale who were graduate students, were upset one year that the physics paper they got to read in French was Einstein's paper on general relativity. And he argued, we have enough trouble with this paper in English. Can you please give us something a little bit more reasonable to look at? I'm sorry, I did French. I knew Spanish, so it was not that bad to get mathematical French. Les Miserables was a good chunk of my studying. I thought it was about cosets, but it was actually only about one. Bad joke. So you should strongly read this. It's a really interesting paper in terms of just how he plays with the mathematics. And a lot of times you get so involved in long technical papers. It's nice to see the paper that just really started the investigation and the power of switching to the complex plane. It would be wonderful if all the zeros had real part, and he's working on the imaginary line, so he's just rotated things a little bit. But it's not really relevant for what I'm doing right now, so I'll skip it for now. It turns out Riemann actually calculated a lot of zeros of the Riemann zeta function and didn't advertise the fact. And decades after his death, someone was going through the library in Göttingen and found some papers with scribbles belonging to Riemann. And noticed, wait a minute, those look like zeros of the Riemann zeta function. And Riemann actually had a better algorithm to compute the zeros than had been developed in the subsequent decades. Just wasn't published and was just sitting lost among the papers. And so it would be very interesting to know at what point had he actually done these calculations. Had he done that before writing in the paper? So if anybody's interested in looking up the history of Riemann's calculations, I will make that an extra credit project. I would love to know a little bit more about that. If people do want to do presentations in the class, for 10% of your grade, let me know because we're running out of class time. All right. So let's just talk a little bit about the Riemann zeta function. So it's defined as the sum over the integers, or equivalently, the product over primes. And this is using the fundamental theorem of arithmetic. Every integer can be written uniquely as a product of primes in increasing order. One is not a prime precisely because we want uniqueness. And so just for definiteness sake, let's just take the first two factors, 1 minus 1/2 to the s, 1 minus 1/3 to the s, and multiply them out. And I'll put the factors corresponding to 3 in different colors so that when you multiply them out, you start to see what's coming. We're never going to get a number twice. And then you can see what comes from the red, what comes from the blue, what comes from the yellow, what comes from the green. And already, just by looking at these two factors, we have 1, 2, 3, 4, 6, and 8, and 9. We're only missing, in the first 10 numbers, 5 and 7. Well, not surprising, those are the 2 primes. And as you put in more and more factors, we will get everything. Nothing ever comes in twice. And so it's a nice exercise to just prove rigorously that this product is equal to the sum when the real part of s is greater than 1. Why do I want the real part of s to be greater than 1? Yeah, that's when it's defined, that's when things converge. We know, for instance, if s equals 1, we have problems. But if we stay with the real part of s greater than 1, everything converges absolutely, and you can justify all of this. All right, so let's look a little bit more at the zeta function. I'm going to look at modifications of the zeta function. So let's define E0 of s to be the zeta function. And then I'll call E2 of s to be 1 minus 1 over 2 to the s times 1 minus 1 over 2 to the 2s inverse E0 of s. Okay. So what does that do? What's this going to look like? Which primes does this not affect at all? If I look at E0 of s, the zeta function, as a product over primes, which primes does this multiplication not change at all? Yeah, all the ones that are on 2. And if you had a prime of 2, we initially had 1 minus 1 over 2 to the s inverse. I multiply by 1 minus 1 over 2 to the s, so that cancels that out. And I replace it with 1 minus 1 over 2 to the s inverse. So this is now 1 minus 1 over 2 to the 2s inverse, product p greater than or equal to 3, 1 minus 1 over p to the s inverse. This is very closely related to the Riemann zeta function. Have I introduced any zeros or poles? When I multiply by 1 minus 1 over 2 to the s, 1 minus 1 over 2 to the 2s. So when is 1 minus 1 over 2 to the s times 1 minus 1 over 2 to the 2s inverse 0 or infinity? So what values of s do I have to worry about? S equals 0. S equals 0. What else? If s equals 1/2, why is that bad?
Maybe it's not, because you got 2 to the s equals 1, so that's fine because that's just where we.
Yep. So s equals 0 is bad. Because when s equals 0, then 1 over 2 to the s is just 1. Is there any other value of s that's bad? No, that's it. So s equals 0 is bad. All other s are good. So we're okay if, say, the real part of s is greater than 1/4. I'm staying well away from 0. So have I introduced any zeros or poles as long as the real part of s is greater than 4? No. All right. What is shampoo mathematics? Lather, rinse, repeat. So what should we look at after E2? E3. So E3 of S will be 1 minus 1 over 3 to the S, 1 minus 1 over 3 to the 2S inverse times E2 of S. Right? And all that's going to do is change the first two primes. And then everything else is going to be the same. Will this introduce any new zeros or poles? No. So in general, let's call it EQ of S would be the product over primes less than or equal to Q, 1 minus 1 over P to the 2S inverse, and then the product over the primes greater than Q, 1 minus 1 over P to the S inverse. And what do we know about the zeros of this function relative to the zeros of the Riemann zeta function? Same zeros. What about poles? So same zeros, same poles as zeta of S. Right? And to be safe, let's say if the real part of S is greater than 1/4. What is the limit as Q goes to infinity of EQ of S? Yes. Yeah, it's just zeta of 2S. Because as we had Q to infinity, we hit every prime, and every prime is replaced now with its square. There's no second factor. Right? So it just converges to zeta of 2S. Does everyone agree with this? I'm just doing it prime by prime by prime. And so when I'm done, I have this function. And everything is nice and well behaved. So same zeros, same poles as zeta of S. Right? Well, we haven't introduced any zeros or poles. Oh, so let's check. So now let's look at zeta of 2. So let's call this E infinity of S is zeta of 2S. So E infinity of 1 is now zeta of 2 is pi squared over 6. And E infinity of 1/2 is zeta of 1. Zeta of 1, which is infinity. So remove the pole. What do you know about the zeros of zeta of 2 of S? What must be true about the zeros of zeta of 2S? Okay. So can you tell me a region where zeta of 2S is non-zero? Not the line real one. We're not assuming. So for the zeta function, I gave you a homework problem. The zeta function has no zeros if the real part of S is greater than. So if the real part of S is greater than 1, there's no zeros. So if I give you zeta of 2S, it has no zeros if the real part of S is greater than. No zeros if real part of S is greater than 1/2. But this looks interesting. We've never changed the zeros of our function. we've just shown the zeta function does not have any zeros with real part greater than a half. What have we just proven? And just because these slides are going to be posted, I will put a question mark there. So did we just prove the Riemann hypothesis? What do you mean clearly not? I'm a showman. I've been saving this. Yeah, this is why I wanted to teach complex. It's been killing me waiting all semester for this day. Because I could use that $1 million. Yes. What's wrong? So could zeros come in the limit? But that's fine if zeros come in the limit. It's really, could zeros have vanished?
All right.
Yeah. What's going on here? What's really lurking in the background? So let me add one extra page. Is the limit of an analytic continuation the analytic continuation of the limit? If you want to get things even worse, we could go for, instead of zeta of 2s, zeta of 3s, and now zeta would have no zeros with real part of s greater than 1/3. So if instead of doing 1 over p squared, if I did 1 over p cubed, I could get that there's no zeros on the critical line. So this is enough to know something is wrong in this proof. This was deliberately proving less than I could to try to sneak it by. So really think about what's going wrong here. As you were listening to the lecture, which steps seemed reasonable, which steps seemed challenging? To me, the real challenge is what happens when you go to a limit. If I look at the functions fn of z equals e to the z plus z over n, what would f infinity of z equal? As we take the limit as n goes to infinity. Just e to the z. And we know this has no zeros. So what's going on? So you've got to be very careful about what properties are preserved under different limiting processes. Right? If you can make this argument rigorous, you are excused not just from all the homework and exams so far, but retroactively and whatever other math classes you've taken. Okay? And you will also get a PhD from the institution of your choice. Okay, if you can make this argument rigorous. I do not recommend spending too much time on that. All right. So what I want to do now is I want to shift to Fourier analysis, in particular to Poisson summation. How many people have seen some Fourier analysis? Okay, I know sometimes it is done in real, and there's a whole slew of different topics you can look at. And so if f is nice, f hat of y is equal from minus infinity to infinity of f of x e to the negative 2 pi I xy dx. This is called the Fourier transform of f. I know there's at least one student here who has a great hat about this. There are at least 3 different definitions you can use for the Fourier transform, depending on whether or not you want to have a positive exponent, a negative exponent, where you want to have 2 pi, do you want to have a square root of 2 pi outside? So depending on what book you look at, you have to be careful to see how they have defined things. How many took 150, 150, 150? Okay, did you do spherical coordinates? What is the angle coming down from the z-axis in math? Phi, and it's theta in the xy plane. In physics, what is the angle coming down from the z-axis? Theta, and phi is the angle in the xy plane. I learned spherical coordinates from the physicists first, and so I have to fight myself every time I'm teaching 150 to have I always have to pause. Okay, it's phi coming down. Because they want to keep theta, because in polar coordinates you have theta. You just have to be careful and always check what you're looking at. One of the most beautiful formulas we have is the sum, and goes from minus infinity to infinity of f of n is the sum, and it goes from minus infinity to infinity of f hat of n if f is nice. So we will define nice later, but I was going to ask, can you give me at least one property that must be true for the function to be nice? Square integrable. I'm trying to think if you actually need square integrable. Well, so the problem with square integrable is I don't know if square integrable is quite enough, because you could have the function getting extremely large over very small regions. We need the sums to converge. So I need to have enough decay in f to make things converge.
Like L2.
So again, I am always happy to do counterexamples. So let me see if I can get one on the fly. Okay, so consider the following. Here's n. Here is n plus n to the delta. Here's n minus n to the delta. And I'm going to find my function to be of height n to the sigma. Okay. So my function is basically going to be a flat rectangle over n. And then the next one I have over here at n plus 1, I'm going to have it similarly high up over here, and n minus 1 like that over here. So I'm going to make the function very large over very small windows. So I can, I think, choose things so that it's going to have a L2 norm that is finite. So I'm going to want to sum n goes from, say, 1 to infinity. The height is n to the sigma, right? If I'm trying to find what is the area in each of these boxes, the height is n to the sigma. What's the base? The base is 2 n to the delta, right? And you want to calculate the L2 norm. And so if you want the L2 norm, I would have to take the height squared for the L2 norm, right? Yes or no? Well, I don't have to really worry about the absolute value because it's, and so if I want to do the integral, this would be the integral from 0 to infinity of f of x squared dx. Because it's only defined near integers, I can replace the integral with a sum. And near each integer n, my function is constant. Yeah, but you can have things that are true almost everywhere, but not everywhere. So if you look at this sum would be the sum, n goes from 1 to infinity of n to the 2 sigma minus delta then I have a factor of 2. So this converges if 2 sigma minus delta is less than, say, -1, right? Because if it's less than -1, say it's like -1.1, then I have a sum of 1 over n to the 1.1 and it converges. So if I choose delta appropriately, can I make everything work? Sorry, this is plus delta, sorry. Sorry, should be plus delta. So I need to choose delta appropriately. If I choose delta for instance, let's take sigma equals 1, take delta equals negative 100. Then you're going to have something that looks like n squared times n to the negative 100. That converges. Or it doesn't. I'm moving over into the delta. I want delta to actually be a very large negative number, so I don't move over that much. What I'm having is I'm having smaller and smaller bands where the function is larger and larger. So as delta is, if delta is like negative 100, I am moving an extremely small amount, and the larger n is, the less I move over. So if I choose this for my function is definitely integrable. But if you look at the sum of fn, n goes from minus infinity to infinity, that blows up. So the problem is, just because the function has a nice L2 integral doesn't mean that the function is bounded. It doesn't mean that the function decays. It just gives you some control over the size of the sets where the function can be wired. And so we can look at how often can the function be larger than the given amount. And I get to walk them today. So we look at how large can the function be? Well, the function can get arbitrarily large, but on smaller and smaller and smaller intervals, because we need the L2 norm to be finite. So when I go back a page and I want this, at the bare minimum, I need these both to exist. So these better exist. If they don't exist, I'm in trouble. So unfortunately, it's not enough to require that the function be L2 to show that that sum converges for all values of n. When I sum over all n, I get a finite number. We need a little bit more properties. Now, if my function is, say, continuous, and I have some information about the first and the second derivative, then that will be enough to prove that these sums converge. So there's lots of different ways of proving Poisson summation. We're going to take a path that allows us to prove a couple of nice results in Fourier analysis that are just of independent interest, that talk about how well can you approximate functions by trigonometric polynomials. And so we're going to develop more machinery than we need for Poisson summation, because these are great results to know. Analysis, real analysis, complex analysis, it is the subject of strange pathological examples. If you want bad stuff to happen, almost surely we can come up with a function that will do that for you. We have the function e to the negative 1 over x squared. All of its Taylor coefficients is 0. So the Taylor series clearly exists and converges, but only equals the function at the origin, which is not that impressive, because the Taylor series at the origin is just f of 0 plus things multiplied by 0 at 0. So you have to agree at the origin. And amazingly, that's the only place where they agree. So we just have to be extremely careful. One of the best pieces of advice I can give you is to think about how to create counterexamples like this. This is why a few classes ago, rather than doing the standard lecture, I said, how do we come up with these counterexamples? How do we come up with these strange cases? A lot of my analysis teaching is inspired by Professor Peter Jones from Yale. I was fortunate to have him, I believe, 3 times, twice for the year-long course on real analysis, and then once for the first semester of complex analysis. And he gave a lot of really good advice. 2 pieces that I strongly recommend you internalize is take a theorem and remove a condition. The theorem should either be false or the proof should be much harder. It is not always the case, but as a general rule of thumb, if you remove a condition, there should be a counterexample to what's going on. The other piece of advice, and this works better the older you are, if you're trying to see if something is true and it looks really, really good, then there should be a name associated to it. Someone should have proven it. And if you don't know any name, then it's probably not true. And so when I was taking my journal exam at Princeton, this is the old exam, I was given an alternate definition of groups. And I was asked, is this also an equivalent definition of a group? And as a typical paranoid student, I had read a tremendous number of algebra textbooks because that was one of my weaker areas. I had seen so many different formulations of this is equivalent to defining a group. What if we only have an identity in the left inverse? What if, is that, and what they gave me was not in any of the books I had read. And so I said, I haven't seen this before. I'm going to guess that this is not an equivalent definition of the group. And they said, good, now prove that you're right. I said, and that means now I have to try to find a counterexample and see, okay, well, what properties do I want that's not included here? So again, the more counterexamples you can come up with, the more intuition you have. You're basically trying to break things and see where can things go wrong. All right, so we talked about counterexamples here. This is one of my favorite problems. When I teach operations research, I love this. So the problem is you have 5 queens, and due to budget constraints, we can only afford a 5x5 chessboard. And we want to put down the 5 queens in such a way that 3 pawns can be safely placed on the chessboard. And here is one possible configuration with 5 queens, and 2 pawns can be safely placed, but only 2 pawns. So the question is, can you find a configuration that allows you to place 3 pawns safely? How would you go about trying to find this? I'm sorry? Good. And so how many options are there? 5 queens on a 5x5 board. How many options? It's not 5 to the 25th. It's 25, choose 5. Right? Because it doesn't matter which queen is on a square, it just matters which squares do you choose. Now you could do a little bit better by symmetry. By symmetry, how many choices are there for the first queen? I'm sorry? I get a little bit less than 7. 6. 1, 2, 3, 4. 1, 2, 3, 4. Basically, the first queen has to be in one of those 6 spots. So there's only 6 options for first queen. Well, I can rotate the board 90 degrees. I can reflect it. It's like when you're playing tic-tac-toe. How many opening moves are there in tic-tac-toe? You might say 9, but if you think about it, there's really only 3. This is equivalence classes: the corners, the middle, the center. And by symmetry, there's only 6 possibilities here. And again, for a computer, 25 choose 5 is no problem for a computer, but this is a general principle if I start giving you a larger and larger board. This problem, how many pawns can you safely place if you have n queens on an n by n board? What's the maximum? There's some beautiful results known, but we don't know that many numbers exactly because the problem becomes a computational nightmare. There is a better way of looking at this. Rather than placing 5 queens on the board so that 3 pawns are safe, what could you do? Go backwards. Place 3 pawns so that 5 squares do not attack. This is duality. This is looking at the dual problem. And for many things in life, the dual problem is often easier. And what's going on with Poisson summation is Poisson summation is really a notion of duality. Rather than studying the sum of a function at the integers, it's sometimes better to study the sum of the Fourier transform of the function at the integers. Now, it turns out if f is even, f hat is just f. Because you could say, well, what if I apply Poisson summation after Poisson summation? Well, if you apply Poisson summation after Poisson summation, you return to where you started. And one of my advisors, Henrik Ivanitz, in one of his papers, applied Poisson summation twice in a non-trivial way and actually got something out of it. So what he did is he applied Poisson summation, and then he worked with that for a while. And then he applied Poisson summation again after that and ended up with a beautiful result. So you can occasionally apply Poisson summation twice. All right, so we will then really start our analysis of Fourier series and Fourier analysis on Monday. Have a good weekend.